Okay, I'm going to make a quick attempt to try to clean up what we did in class today. And what we started with was the observation that the derivative of the area gives us our function back. Now, this is kind of the question that came up, and what I should have done was I should have fixed it in the following manner, but I think I didn't, so I apologize. When we're talking about taking the area from A to someplace, we're kind of looking at this. We're saying, like, here's A. We could change it to B. I'm going to do it the way your book does it, so you can use the same notation. We're going to go from A out to some x value. Oh, here's our function. So what we really want to do is we want to use a different variable in here. So I'm going to do that now. I'm going to change that. We can change it to anything we want. It doesn't matter. We could always change our variable to something. X is an arbitrary choice. Your book chooses t. So we're going to take the derivative from a to x of the f of t dt. Sometimes mathematicians like to call this a dummy variable. It's not very nice. Is equal to the f of x. And it's the f of x because we're taking the area from a to x. This area under here, the area is a function of the x value. That's why this has to still be x. That question came up today as well, and I'm not sure I handled that very well. Okay, now we're going to take the antiderivative of both sides. So I'm going to just write that out. I'm going to take the antiderivative of all that whole mess. Antiderivative of the derivative of a to x f t dt. The antiderivative with respect to x is equal to the antiderivative of f of x with respect to x. So all I did is transcribed both of these entire sides inside an antiderivative. And I think the part that maybe actually went smoothly today was that the antiderivative of the derivative simply gives you back what you started with. Hi, so we have a to x f of t dt is equal to the antiderivative of f of x dx. So what we're going to do now is we're going to relabel, we're going to invent some notation. We did this as well. Big F of x is equal to the antiderivative of little f of x. And we can always add a constant of integration so that this becomes the antiderivative from a to x f of t dt is equal to big F of x plus c. Okay, and then I'm going to leave out the next part so it doesn't get too cluttered in here. I'm just going to summarize it. Check your notes, check your book. If we let x equal a, then we find that c, that's another point. So we plug in another point to solve for our constant. C is equal to minus the f of a. And plug that back in over here, we get that the definite integral, that is the area underneath the curve, is equal to the f of x minus the f of a. This is quite useful. Let me show you why that's quite useful with the example that we had in class, all quick-like. We had 0 to pi fourths, the cosine of 2x dx. What this says is we can evaluate this area by taking the antiderivative. The antiderivative of the cosine of 2x, of course, is, maybe take that aside and make sure you can do that, 1/2 cosine of 2x. Sorry, that's not right. 1/2 the sine of 2x, of course. So the antiderivative of the cosine of 2x is there. So the fundamental theorem of calculus tells us that this definite integral must be equal to 1/2 the sine of 2x evaluated at the endpoints pi/4 and 0. You'll see this notation in your book, which is 1/2 sine of pi/2 minus 1/2 sine of 0. Sine of 0 is 0. Sine of pi/2 is 1. So this area is equal to exactly 1/2. And that's how we use the fundamental theorem of calculus. If this is confusing, don't worry. You're joining a large population of people who found the fundamental theorem of calculus to be confusing at first inspection. Don't give up.